So, okay, happy to be here in another Pichia edition. I think it's something, thank you, very familiar. So 80% of the people, we are always more or less the same. So happy to be here again. Next, please. Okay, some brief, maybe most of you know us, but just a brief review about us. We are manufacturers and providers of fermenters and bioreactors from laboratory scale to large scale, from 1 liter to 5,000 liters. And also we are providers of cross-flow filtration system from laboratory scale to large scale. Next. So we have offices in Spain, Germany, and the States. So we have global presence. Okay, so just a brief take a look. Some history. The first fermenter as a deep tank mechanical agitated fermenter has more than 100 years, more or less, as we know. So one history tells that Pfizer developed the first deep tank fermenter according to a need of citric acid production due to the limitation of lemon production during the First World War. And then, thanks to this need, was developed the first deep tank fermenter. We know nowadays as a stable fermenter for a precision fermentation. So it's a well-established technology, a well-known technology. And then now, 20, 30 years ago, was developed the first single-use bioreactor. So during the drug manufacturing, the companies receiving serum from clean bags, they saw that it was a good idea to use a bag directly for the cultivation of the processes. So saving time in cleaning. So with this idea was developed the first single-use bioreactor 20, 30 years ago, more or less. Okay, so next. Then, just to summarize the single-use bioreactor types according to the upstream part, because the single-use technology has grown since then in all the process of the manufacturing process, not only in the upstream part, also in downstream part. So focusing in the upstream part, we can find 5 main types of single-use bioreactor: steel tank, perfusion bioreactor, orbital shaking, and rocking motion. And then the rocking motion is the type of single-use bioreactor we have. So small details make the difference. With the typical rocking motion is like a wave, but we add a second movement, as we call the two-dimensional rocking motion. So just with the small introduction, this small difference, the KLA is increasing significantly, more than 300 hours -1, because it's simulating the movement of the waves of the sea, and then with this movement of the waves of the sea, trap the air and increase the mass transfer oxygen in the system. So for that reason, our objective is to differentiate its equipment, not for mammalian sake, because it's the typical. So we want to focus our goal to apply to use this equipment for microbial with a high demand of oxygen consumption. So basically, it's the same system that I fermented, the 3 main parts: the bioreactor, the vessel, in this case it's a bag. At the bottom you have the probes, the pH, dissolved oxygen probes, already installed and still just one use. Software and the bioreactor control unit. And in this case we have 1 liter, 12 liters, and 120 liters for microbial application. Next. Okay, so the objective of this study was to compare a well-established and developed process that we have with a stable mechanical fermenter at pilot scale for the production of, with a strain of Pichia, producing the enzyme Candida rugosa lipasa under graph promoter, a methanol-free system, applying with the single-use bioreactor, the cell tiner, and then comparing the key performance indicators of the process. Next. So one of the peculiarities of this back system is the flexibility. And then with this idea, we developed a tool, expansion channel, to reduce the working volume, the initial working volume of the bioreactor. And then this way, we can prepare in one step, using the same unit, the inoculum. And then in the study, we include this expansion channel to prepare directly the inoculum from the working cell bank, inoculating into 250 milliliters of GPD, and then from a 12 working volume liters back, we can reduce still 100 milliliters working volume. Okay, so next. And then this is the setup of the comparison at pilot scale, comparing both systems, the disabled mechanical fermenter and the single-use system, and then replicating the conditions that we have well established in the mechanical agitated fermenter, in the single-use bioreactor. So mainly pH, temperature control, and the fed batch strategy for the exponential feeding, but with some differentiations according to the dissolved oxygen control, because in the case of the mechanical agitation system, we have often to apply cascade control of the agitation, and we increase the pressure instead to use oxygen enrichment to maintain the dissolved oxygen over 50%. And in the case of the single-use back, we need to change our mind and the text transfer parameters for agitation, because in this case, we need to consider the frequency of the agitation at this scale and also the angle, because considering the system of the motion, the rocking motion, we need to also consider the angle, because in the case of microbial culture, to increase the dissolved oxygen, the angle is wide, is higher, but in the case of cell culture, we restrict the angle. Okay. And also, we include the oxygen enrichment, and the same way that we include overpressure in the mechanical fermenter, agitated fermenter, because the maximum pressure can support this type of bags, 0.1 bar. Otherwise, the bag can explode, and I can assume that explode, unfortunately. Okay, so next slide. Results. Okay, so regarding the using the tool of the expansion channel, so besides to accelerate the growth comparing to the safe flash, because we often to apply 24 hours for the safe flash, and then in this case we should propagate at 12 hours, because basically it's like a microbioreactor. We obtained real-time information of the process, as the way we could see the optimal moment to propagate, so following the exhaust CO2 and the evolution of the pH. And then here, following the pH, when increase and when decrease the CO2, were the optimal moment to propagate. And then besides to reduce timing from the safe flash, so besides the reduction on time also was an advantage that we have real-time information for the process, and then to optimize and reduce time for propagation. Okay, so next. So in the pilot scale, regarding the pH control, is if something I have learned in testing technologies during all these years at Bionet is we don't assume that the basic controls is going to work at that we want it to be. So besides the pH control can be something very basic, it's necessary to adjust many parameters like the PADs or whatever. So finally, we maintain the control with the backup we wanted, because for me, honestly, at the beginning, we thought that it's going to be difficult, because with the mechanical agitation, of course, we have very well optimized the control, and then in this case, we obtained also a similar profile to maintaining the pH. So in this case, we add in ammonia, sorry. We use it as submerged port, just to avoid losses of the ammonia during the addition. Because mainly in this case, the gas is not sparking through the bottom, so it's adding to the top of the bag, and then just to minimize the losses of the ammonia, we use this submerged pot. That will be the same pot if will be used for methanol addition in this case. So just to add, we repeat these other experiments adding ammonia during the top phase of the top part of the bag, and also the losses were not so high, considering that at high demand of base during the growth, the agitation is quite high, and then at this way, touching the media, the top part of the bag, trap the ammonia and then minimize the losses. So works also. Okay, so next. Okay, the dissolved oxygen control. This is the most challenging and questioned control in this case. So here we are obtaining a similar profile of the dissolved oxygen, and then when we reach the value of the 30%, the agitation in this case increase automatically, maintaining the aerobic optimal condition of normoxia of 30%. So in the same way that in the mechanical agitated fermenter, the pressure increased just in order to maintain the dissolved oxygen over this 50% of saturation. It was the equivalent that also in the single-use bioreactor, adding some oxygen enrichment at 0.25 ppm. And then regarding the optical density, we reached a similar values of final optical density with exponential feeding that we applied. So that considering this high optical density, we don't find problems to maintain optimally the temperature, regarding that with this high viscosity, the heat dissipation can be a problem. So we took the samples offline, of course, periodically, because in the case of the fermenter, the F2, we had an online optical density probe, and then we could monitor in real time the optical density, linearizing, of course, and then we obtained a similar profile in both systems. Okay, and then regarding that, we don't have some options comparing with the sterilizable fermenter with this type of single-use bioreactor. We are using also to monitoring the growth in real time, because in the case of the Celtiner, we cannot use an optical density probe in the same way we use it in the pilot ferment, in the sterilizable fermenter. So using the exhaust gas analyzer following the CO2, we could monitor the growth and then also calculate in real time the specific growth rate, linearizing the values of the CO2. And then in theory, the specific growth rate of this strain is 0.05, so we obtained a similar value. So this is something interesting to maintain and continue to improving this monitoring to obtain more information in real time, using non-invasive and inserting any instrument and probes in the equipment. Okay, so next. So just to finish, we obtained close than 100 grams per liter of dry cell weight, and a similar total protein concentration of Candida rugosa lipasa, and a similar expression levels in comparing the reference, the control, the F2 fermenter with the Celtiner single-use bioreactor. And so this is the movement, dancing movement of the single-use bioreactor. So this is a real picture, okay? This is not a beautiful one you can find in the catalog. So, okay, so finally when you are testing technology, this is the real. And just as you can see, the movement is not like a wave, and then for that reason, our goal is to use this equipment with this two-dimensional rocking motion for microbial culture. So, okay, next. So this is high viscosity, the final broth, but it's difficult to see. So, good harvest. Okay, and next. So just to summarize, Some advantages and limitations of both systems. In the case of the sterilizable fermenters, of course, advantages we have reusability and robustness, and it's a very well-known technology and with many options of volumes for large-scale production. So advantages of this system is necessary to clean, sterilization, risk of cross-contamination, also the infrastructure, the capex, and then for the piping, boiler constructions in the case of the OPEX, energy, labor, and maintenance. So in the case of the single-use bioreactor, the limitations can be for its nature, the long-term storage, because it's a average cell life, the time that you can use a single-use bioreactor, 1 year more or less. Also the supply, so unless you have a very good supplier, and then also you need to ensure that you have a good supplier for bags. And also one limitation can be, of course, the cost of the consumables, the bags, because in some, depending on the sector, can be expensive or not. And advantages, of course, and also one limitation is the lack of information. It has been in applications, mainly in microbial, has been one of the aims of this comparison, to learn more about this type of system. And then advantages, of course, so time, so you save time because you don't need to clean, sterilization. Also, you are reducing needs in the infrastructure because you don't need pipes, boiler, steam, and also for validation because you don't need to validate the claim. So for pharma industry, it's a requirement, the validation of the claim, so which is considered clean, and then is one of the advantages. And then one also of the limitation of the single-use bioreactor is the capacity, the large scale, the volumes. So for that reason, in some sector, depending on the sector, the maximum working volume you can reach with this type of system cannot be applied, because for pharma sector, in many processes, you find nowadays, of course, single-use bioreactors, no problem, because the final working volume covers perfectly the production scale. But for other sectors, like the food sector, ingredient sector, can be a limitation, the large scale, the working volume you can find at commercial scale with this type of systems. So it's one of the advantages of the sterilizable fermenters. So one thing that we are finding nowadays is an increasing hybrid combination of the system that we have clients using this single-use bioreactor in the seed train for the propagation of the large-scale fermenters. So it's very useful because in the middle you are reducing risk contamination and timing, and you can still use the large-scale fermenters for production in these sectors, alternative to not only for pharma. Okay, and next, and the last. So just to remark one conclusion. So we could optimally cultivate at high cell density Pichia pastoris in this type of rocky motion single-use bioreactor, the cell tiner. Just to add another last comment, remember, this is not a whey bioreactor for mammalian cells, so our focus is to use this one with these different movement to microbial applications. Thank you to my colleagues, my students in the lab. So otherwise I cannot do anything. Okay, Ana Fuensanta, and also the support of Tupku. She is our Chief Scientific Officer in single-use bioreactors. Okay, thank you.
Thank you very much.
Thank you for your nice talk. Got one question. So, well, first of all, a comment. It's kind of amazing to see that in a shake bag you achieve the same thing as in a stainless steel reactor. That's the first time I see it, so that's well done. My question is, how high can you go with your bag? So is that, well, volume-wise, is that past 120 liters? Can you go up to 1,000 plus?
Right now, we only can reach 120 liters with our bag.
But based on the data you have been collecting, can you do a projection on how high you can go with your volume?
No, by the moment, no.
Okay.
So we are exploring, for example, using this bag for continuous processes. And then we want to combine also, for depending on the process, a continuous, because you can reduce increase the productivity and then reduce the working volume if you can implement a continuous process. But for many sectors for microbial, we are promoting the use of this bioreactor for seeding, as inoculum. And then for food and ingredients, this volume, we have a client using this bag to inoculate 15,000 liters to produce lysine. And so, by the moment, we maintain this maximum working volume. No, we don't have plans for.
Okay, thank you.
Thank you.
Thank you, Juan. Can you please comment on anti-foam usage during the process in both fermenters?
We don't use anti-foam in the single-use bioreactor. Good point. Yes, the big problem, because in this case, you don't have mechanical agitation and the gas is not sparging, it's throw overlay. And then we don't use anti-foam in this type of single-use bioreactor. So it's one advantage, of course, you don't have foam problems. And also for downstream, you are avoiding this problem.
I have one last question. So I usually see people use those bags to grow the mammalian cells. This is my first time to see it can be used to grow Pichia, so it's very impressive. And so is this like CD20, is it like design exclusive for grow high density cells like Pichia and coli? Can you repurpose it for use to grow like mammalian cells, like CHO cells, especially like for lab like us, we have multiple expression platform. So if one bag for all kind of cells would be great.
You can apply to another cell lines. Okay. So changing the bag, so you have other options. So changing the filter capacity and also changing the angle inside the bioreactor, the movement.
You can change the mode of the rocking mode.
Yeah. So you can just changing a couple of points inside the system, and also using a different bag that we have already, this bag for cell culture. You can use the same one, the same system for cell culture. In fact, right now, we are doing also cultivation of plant cells. So one of the PhD students I have in the lab, she is cultivating Nicotiana bentamiana and broccoli cells, like plant cells, with this type of, so just changing these couple of parameters in the unit.